Alrighty, welcome back to operating systems. So today, nothing testable, a little fun lecture, kind of act as review, or maybe as, an introduction to a networking course or just how we use our computers. So we get to talk about sockets today, just another form of IPC, but instead of IPC across processes on the same machine, it's more fun because the processes can be running on other machines. So, review, we've seen pipes, everyone's favorite thing. We've seen signals, everyone's also favorite thing. We talked briefly about shared memory, didn't have any actual examples of it, but those are all three different ways of having inter-process communication. So, those all assumed that all the processes are on the same physical machine with shared memory. They're sharing memory, so they have to be on the same physical machine. Pipes, basically another form of shared memory, just managed by the kernel itself. And then signals, we have to have a process ID to send a signal to another process, so they also have to be on the same physical machine. So sockets, they're just another form of IPC between physical machines, typically over a network. So, has anyone ever used a web browser before? Hopefully. So, if you used a web browser before, they use sockets. That is the only way to communicate between different computers over a network. That is what it's called at the kernel level. You might call it different things, might have different protocols, but at the end of the day, whenever you do a system call, it is a socket system call. So, usually with servers and sockets and internet connected stuff, there are two ends. There's usually a server and a client. And this lecture, if you have any general questions about how things work, feel free to ask them. This is more of a fun lecture. But in your server, generally they follow 4 steps to use a socket. So these are all system calls. They all have the usual C wrappers where it'll return -1 if there's an error, set error no, all of that fun stuff. So the 4 steps, if you are the server, is first you have to create a socket using the socket system call. Very clever name there. And then, well, a socket by itself isn't that useful. That's very generic. You have to attach it to some location so that someone can actually connect to it. So the second system call is called bind. That will attach it to some location depending on what type of socket you want to have. So it could be a file, it could be an IP address and a port, could be an IPv6 address, something like that. All types of different options we have. Then the third step is you have to indicate to the kernel you are accepting connections. So you have to listen to it, and internally this will also have the kernel keep track of a backlog of waiting connections. So there'll be some type of queue limit that you can optionally set, or you can just have it manage the queue itself. But basically you can set a limit as to how many incoming connections you will actually let sit there and wait for you to, in step 4, accept them. So that returns the next incoming connection for you to handle as a file descriptor, and then you can read and write to it just as a normal file descriptor, except the bytes are coming from another machine on the network. So if you're the client, that is probably you in a web browser. So the server is more like google.com or whatever other web server. And then your client's more like a web browser. They only need to follow 2 steps to use sockets. So they just do the same socket system call to create the socket in step 1. And then in step 2, they just connect to it. So they connect to that same location. And now the socket is eligible to send and receive data, so you can do the write and read system call on it. So the socket system call, it has 3 arguments, sets like the protocol type of socket. So domain is general protocol. You can sub-specify it with this protocol argument here. Generally, this one's not used, and it's just set as 0. So basically, there's just 2 arguments. So there's domain, aka how I expect to connect to this socket. So the 3 main ones are AF Unix, so that's for local communication, so on the same physical machine. And then if I want to use the internet, well, there's INET, that's for IPv4, So normal IP addresses like 8.8.8.8 or something like that. And then there's INET v6 for IPv6. So that's just longer IP addresses because we've ran out of IP addresses. This IPv4 is only 32 bits, and everyone connects all their toasters to the internet and everything like that. So we've ran out of IP addresses. So we need INET v6, which is just a 64-bit version. So the type, usually it's one of two options. It's stream or datagram. They're very generic names that you might not have heard before, but really stream just uses TCP, if you've ever heard of that before. So what TCP is, well, networking is very complicated, as you will figure out in the networking course. Just because you send packets or send data to another machine doesn't mean they'll all arrive in the same order, doesn't mean they'll even take the same route. So if I connect to a machine in Texas, maybe some of my packets go through New York, maybe some of them go through Los Angeles. You don't know what order they'll set. That is all stuff in the networking course, but the whole goal of TCP is to kind of hide all of the networking ugliness so that any data you send it will be received on the server in the same order. And it will also form a persistent connection between the client and server so that if one disconnects at any time, you will know the connection has been lost. So this is reliable, but maybe slow because it needs to do some extra bookkeeping to keep track of what packet should be sent in what order and reconstruct it at the other side and actually acknowledge that there's some type of connection. So the other option is called UDP. Those are also datagram sockets, and those just send messages between the client and server. No persistent connection whatsoever. It's really fast. There's no overhead. You just send packets to a server, but they might arrive in a different order or be dropped completely. You just send off a packet. You get no acknowledgement whether or not it's received or not. You just kind of send it and hope for the best. So this is really fast, but of course unreliable. So you might use this for things that retrying sending information doesn't really make sense. Like for streaming video or something like that, if I miss a frame or whatever, it doesn't make sense to resend it because it's already happened. So probably just will count as a drop frame and just keep on sending more and more and more. If it gets dropped, whatever, you just skip a frame. Or if it's like a game or something like that, you know, the world state probably changed by the time you would resend it anyway, so you wouldn't bother to resend it. So most video streaming and games and stuff like that use UDP. Other web servers and things that need to be more reliable use TCP. So if you connect to google.com or something like that, that would be TCP or the stream socket. All right. The next system call is this bind system call. So it takes as the first argument the socket and then some address you want to bind it to. Because it is C, you have to use this kind of ugly struct socket address, which is just a pointer to some structure, and then the structure changes depending on what you want to connect it to. So the three major different family types all have their own struct. So if you want to use it for local communication or a Unix socket, it's sock address underscore un. Short for Unix. Again, I don't know why they had to shorten this to like the 10th degree, but it's usually just a path, so it's a file name, and we'll see an example of that I wrote. And then for socket address in, supposed to be short for INET. Don't know why again, that's just an IPv4 address like 8.8.8.8, which is one of Google's servers. And then like there's in6 or INET6 for the IPv6 address, and they look something more ugly like that. Usually they're done in hex and divided into 4 little chunks there. So the listen system call, that sets the queue length for the server for incoming connection. So it just takes a socket as the first argument, and then this backlog, or how many incoming connections should the kernel hold on to until it starts just dropping connections. So if you just give it 0, the kernel figures it out for you. You can just use the defaults. And for most of it, just the defaults are fine unless you really know what you're doing, in which case you're probably using a web server written by someone else anyways. So the last one is that except system call that blocks. So this is a blocking system call that blocks on the socket here until there's a connection. This address and address length, well, those are the same things as in the bind system call, so they are actually optional. So if it's a stream socket that has a persistent connection, you don't need to use these at all. It's just if you want to skip the bind step for a datagram socket or a UDP socket. So for us, we can just ignore the other fields. It's just a blocking system call on the socket that whenever it returns you a new file descriptor, and then that file descriptor represents that connection to whoever connected to it, and you can do read and write system calls to it to get information from it or send information to it. All right, the last one is for the client. It just needs to use that socket system call and then the connect system call, and it looks exactly like bind. It has to match. So it just has a socket address, and then because it's C, you have to tell it the length of that structure. But other than that, it's exactly like bind. If the call succeeds, then the socket file descriptor you gave here can now be used as a normal file descriptor. It has connected to a server, and you can do a read and write system call with that file descriptor now. So now we can write a little server here. So, VM. So here is our client code. So our client code, I just wrote this little function that takes care of checking error no like we usually do. And then here I just say my socket path I want to connect to. I'm just going to call the file example.sock. And then in main, what I'm going to do is create a new socket. It's going to be that Unix type. It will be a stream socket and then protocol 0. So that's just unused. So I'm using that reliable one that hopefully gives us the data in order and handles all of the complexity of dealing with networking stuff. So of course we check for errors. If there's an error, we just exit out with the error. Otherwise, we need to connect to some location. So how we would do that, since it's a Unix socket, we have to use this socket address _un. And then I do equals curly bracket 0 to 0 initialize the whole thing, so I don't have uninitialized memory. Make sure I zero out the entire struct. And then I have to set the Sun family, so that is just what type of address this is. It has to match the domain here of the socket, and that's the only way C can figure out, hey, what is the structure of this random block of memory you have given me. It expands to just 1, so I have to set it off at AF Unix, and then it just needs a path. So in this socket address, I guess Sun Microsystems was the first one to do this, so they prefixed everything with Sun _. So I don't even know if they exist anymore, but hey, because they did it in the 70s and we can't change things once we expose it to the user, it's like this forever now. So Sun path is just the name of the file you would want to the field that holds the name of the file you want to connect to. So I just do a string copy. I copy in the socket path, which is just that example.sock. That's the file I want to connect to. Then all I have to do is do the connect system call with the file descriptor I got back from the socket, and then I give it the address of that socket address structure I got, the size of it, and then check for errors. If no errors happen and I've successfully connected to it, then I can do read and write system calls to it as before. So I could just declare a buffer that's the size of a page, do a read system call, just read all of the data we can, and then here I'll just print off whatever I received. So nothing fancy, just does a read over and over again, fills in the data, and that's it. And then I just close it. So if I run this program right now, if I just run this program right now, there's no server running, right? So nothing should happen. So if I just run this right now, I get an error from Connect saying that no such file directory. The example.sock doesn't exist. Moreover, it is definitely not a socket. So I need two sides. I also need a server. So in my server, all I do is, well, same thing. I just have a global variable here called FD because I'll clean it up in a signal handler. But here I do the same thing. I do a socket system call, say it's AF Unix, it's a stream socket like before, set up the exact same socket address structure, give it that same socket path, but now since I'm the server, instead of the client, I bind instead of connect. And then after I bind, I have to listen to tell the kernel, hey, I would like to accept new connections. And then this is basically what a web server looks like. It's just while true, I just accept. So accept an incoming connection. This is a blocking system call, so as soon as someone connects to it, it will return a new file descriptor that represents that connection. So I can, of course, check for errors. Other than that, it is now a file descriptor. I can, in this case, I'm just going to write bytes to it. If this was a web server, right, it would send you the page you requested or whatever. In this silly example, I'm just going to send the string hello there with an exclamation mark. So I'll just do a write system call to that connection. Just give it the string and the number of bytes in that string. Check for errors. Make sure that I write the whole length. And then other than that, I can close that file descriptor representing the connection because I'm done with them right now. I don't want to send them any more data. So now if I go here, and I run the server, right? Server looks like it's not really doing anything because, well, if I straced it, it would be just blocked on that accept system call, right? It's just waiting for someone to connect to it. So if I flip back over to another terminal here, and I look here, I can now see there's this example.sock lit up in magenta to indicate, that's how it's indicated to me in my terminal, that it is a special socket file. So it doesn't actually exist, doesn't actually consume any space. It's just a name that the kernel knows, hey, that file name is connected to the socket. That is what the server is listing on. So now if I run the client now, the client should be able to connect to that server. So it connects to that server, and then it receives a string that the server sent to it, hello there. And I can connect as many clients as I want, right? Because every time through, that server just accepts the connection, sends the string, closes it, and it just does that over and over and over and over again. All right, cool. Any questions about this or fun things you want me to do? Looks neat, huh? That's the internet. Yeah, if you strace your web browser or anything like that, this is how it works. It essentially does the exact same thing as this. Other things I could do. So here, in order to clean up correctly, then I might have to use a signal handler. So in here, my handle signal will make sure that, hey, I should actually gracefully quit if I get sig init or sig term. So I should close that socket. So I'd close that file descriptor represented by the socket. It's just a global variable. And then unlink socket path, that actually removes that example.sock name. So it doesn't appear in my directory, and I can't actually try and connect to it. So if I go to the server here and press Control-C, it'll clean up everything. So if I ls here, that example.sock file now no longer exists. So if I go back to the client and try and connect to it, I get no such file directory, can't find anything like that. Other fun things. So if the server is running and say, I don't know, say someone wants to be violent and kill -9 it, then it won't clean up anything, right? It'll just brutally murder it. It's dead, and it won't clean up that file or anything like that. So that example.sock will still be hanging around. So now if my client tries to connect to it, it will get a little bit further, but it will fail that connect thing and it gets connection refused, which is an error you've probably seen if you've used the internet before. Same idea. You're trying to connect to something, it is not available, the name exists, but you try and connect to it, you get a refused. So, the internet. All right, any questions about that or any other fun stuff you want me to do, or we are just ending hella early? I guess it's midterm/lab time anyways. Yeah?
Hypothetically, if you try to access a file, a socket file on a different server, like say through SFTP or something, would it work?
So if you tried to access a different file through SFTP,
Like the sock file through.
The sock file, yeah. So the sock file, even if you could see that file somewhere else, it is associated with a socket through the running kernel, so you wouldn't be able to actually connect to it. So you would have to use like iNet or something like that to actually connect to a different server. The file has to be on the same machine for that.
So it's just like a name.
Yeah, it's just a name. If you don't have an internet or something, you still want to use a socket. People usually use these just to run a server on their own machine and test things out like that. Yeah?
What happens if you try going into the example.sock file in VS Code?
If I try going into the example.sock file in VS Code, well, so if I look at it here, its size is 0, so it doesn't actually contain any information. If I try looking at VS Code, it just says unable to read the file because it's not a real file. An error occurred. Unknown error, I guess they don't know what a socket is. But it's not a real file, it's just a way for the kernel to kind of cheat a little bit and associate that name with the socket that it actually knows what it's supposed to connect to. But yeah, for most of the things for a real web server, right, it would just use that iNet thing. You would have an IP address, and then that's how the internet works. So if you wanted to, if you knew Google's IP address, you can just set up a socket, you can connect to it, you can send Google any type of information you want and just see what happens. But it'll probably be like me walking up to you and just talking Icelandic. You'll probably just ignore me. So Google will probably also ignore you. All right, any other questions? Nothing about how the internet works? All right, well, that's your networking class for later. So I'll just wrap up quickly since I guess we're tired and this will be a new record. So instead of read and write, there's also special system calls that work directly on sockets called send and receive. Basically just adds a few more options that are specific to networking. So there's some examples like message OOB, send out of bound or out of band, so send some priority data. Peek, so I can look at some data without actually reading it. So if I do another read system call, I would get a repeat. So maybe I just peek at it to look at the data to figure out in my program where it's supposed to go, and then something else does the read system call. And then there's this weird thing, don't route, so send data without routing packets. That might seem like a weird thing to have if you expect routing to happen if you're connecting to a web server or anything. Basically, why this is here is because, well, routers are also done in software, so you need a way to write software for a router, and you don't want your router to route, otherwise you will probably get yourself in an infinite loop or something like that. So if you need to implement a router stuff or something like that, you have to use this don't route. You probably will never use any of these except for message peek. There's also send to and receive from that take an additional address, and the kernel will just ignore that for stream socket since there's already a persistent connection. But if you strace, so like I strace ping before, I see send to and receive from, but they're basically the exact same thing as read and write. So it's kind of a prelude to your networking course. So you perform networking through sockets From the point of view of this course, you already know how to use them. So they're just IPC across physical machines. They need an address, two types, stream and datagram, or TCP and UDP. And servers, if you're the server, you need to bind to an address, listen, accept connections. If you're a client, you just need to connect to an address. Other than that setup, they're no different than any other form of IPC we've seen before. Just a file descriptor, send and receive bytes. And if you want to learn more about how data actually goes over a wire and gets routed from here to Los Angeles or wherever, that's a preview for your networking course. So with that, I'll wrap up, hang around here for questions or anything like that. So just remember,